So we've taken a look at the adjustable spinner applet. That's just a convenient way of simulating playing a random game a whole lot of times very quickly. So we're going to use that now in a couple of examples for what's called expected value. And expected value is basically just the average value that we would expect from playing some game of chance over and over again. Right? So if we were to play a game at a casino over and over and over again, how much would we expect to win or lose per play on that game? So we start with simulations where we pretend as though we've played the game a whole bunch of times, and then we calculate the average value to see how we would have come out had we decided to play that game a lot. We're going to take that idea of simulation and combine it with the law of large numbers to get a really nice, concise formula for calculating expected value without needing to do all of those simulations. So there's one example already worked out for 1,000 spins that's in the notes. The next example uses 5,000 spins and asks us still to find the average value of playing the game 5,000 times. Now the way the game works is we have a spinner that's got red and blue on it. The red is about 55% of the area and the blue is 45% of the area. If we spin and land on red, we win $10. If we spin and land on blue, we lose $10. We play 5,000 times and to figure out what our average winning or loss would be. All right, so in this simulation, we spun 5,000 times and we got red 2,755 times. So we won $10, 2,755 times. But we also landed on blue 2,245 times and lost $10 each time. So we subtract $10 times the number of times we lost, and then all of that gets divided by 5,000, which was the number of times we played the game. Right? We won a lot, we lost a lot, and now we're going to figure out what our average winnings were. Now, if this is a casino game, we would expect average losses, but this is a made-up math class game, so we're going to win. All right, so I take 10 times 2,755 and subtract 10 times 2,245. That's 5,100. And I divide that by 5,000 for the number of plays. And I get an average win of $1.02. So this would be the answer to that second example for the average win if we played this spinner game 5,000 times and won 2,755 times and lost 2,245 times. Now, it would be nice, right, if we could find the values, the average values of playing games of chance without having to play 5,000 times to figure that out, right? That could be an expensive lesson. So what we're going to do is take a look at the formula we use to get the average value, which is just our total wins or losses divided by the total plays. And we're going to combine that with the law of large numbers to produce a really important and really nice formula for expected value for a game. So start off with what I've got in the notes already. Our average value is the amount we win times the number of wins. And then of course we lose some, so we have to deduct the loss for each, the money for each loss times the number of times we lost. And then we divide by the total number of times we play. So if we reorganize this just a little, I can rewrite it as the amount we win times the number of wins over the total plays, the total trials, minus the amount for a loss I've done is something that we have to remember that we can do from fractions, right? If you have the same denominator, you can pull those apart. So what I've done is just written this one fraction as two separate fractions that have the same denominator. And then I just collected part of the numerator, the number of wins, divided by the denominator, total plays. But mathematically, this second line is the same as the first, right? So we just use some properties of fractions and multiplication to make it look a little bit different. But it looks different in a way that's really important, because if you recall, what we have here is the number of times a win happens divided by the total number of plays. That's the relative frequency of a win. And similarly, the number of losses over the total plays, that's the relative frequency of loss. So this is really the amount we win each time times the relative frequency of a win minus the amount we lose for each loss times the relative frequency of a loss. And now that's an important observation, because the law of large numbers says that if we play enough times, the relative frequency of a win is the same as the probability of a win. And the relative frequency of a loss is the same as the probability of a loss. So when we play enough times, in the long run, we get the expected value. And the expected value is the amount we would win times the probability of a win, and then minus the amount we lose times the probability that we lose. Well, if we know the probabilities beforehand, the probability of a win and a loss, we can use this formula to find the expected value, or the average long-term value, without ever having to play the game. So for this particular spinner game, the amount we win is $10 times the probability of winning. That's 0.55, because the red is 55% of the area. And then the amount we lose times the probability that we lose, which is 0.45, because the spinner was created, right, with blue at 45% or 0.45 probability. And then what we see is, well, $10 times 55 minus $10 times 45, that's 550 minus 450, and that is $1. So the expected value of the game is $1. If we played enough times, that would be our average win or loss, in this case a win. So notice that first off, the value we got from simulating 5,000 trials is really close to the actual expected value, right? The sort of random simulation of 5,000 trials had us win an average of $1.02. The actual average, if we kept going, would be $1. So this is a game that's favorable to us, and we can figure out what our average winnings or losses would be without having to play. So let's take a look at the next example as well. So this is one we're going to do without simulating, which we certainly could do if we needed to. So this is a game that's a dice game. So we've got a fair six-sided die. We roll a 1, 2, or 3, we win $5. 1, 2, 3. very unlucky and we roll a 6, we lose $10. All right, so the general process for finding expected value, and then there's a little bit of notation there to represent that, is you take the amount you would win for each situation and the probability of that happening, multiply them together, and then take the amount you would win in the other situation, find that probability, multiply them together, and then subtract the amount you would lose times the probability of losing. So the expected value is going to be $5 times the probability of a 1, 2, or 3 plus $8 times the probability of 4 or 5 and then minus $10 times the probability of 6. So we have to use the fact that it's a fair 6-sided die, and we'll get expected value is $5 times 3 ways of winning $5 over 6. So that's 3/6 or a half. We have $8 times 2/6 or a third. And $10 times 1/6. So I'll get my calculator to do the arithmetic for me. So I get 5 times 0.5 plus 8 times 0.333 minus 10 times a sixth. So the average value for this game also turns out to be positive. It has an expected value of $3.50. So a point that's made in the notes that's worth repeating is that, right, the idea of the average value doesn't, or the expected value doesn't mean we actually expect to see $3.50 on any particular game, right? We either win 5, win 8, or lose 10. So we never actually win $3.50. This just says if we play enough times, on average, that's what we're going to end up with. We'll win 5 sometimes, we'll win 8 sometimes, we'll lose 10 sometimes. But the average is $3.50, and it comes from just multiplying the outcomes times the probabilities and adding them all together. All right. So in the next short video, I'll do the warranted example, which is a little bit more involved, but uses the same formula and hopefully will be interesting. So that is all for this one.